Something that shouldn't exist just erupted on an object from another star. Not gas, not dust. Ice volcanoes, erupting violently in the vacuum of space on a visitor that travelled light years to reach us. And what's triggering them? That's where this story gets uncomfortable. Right now, as you're reading this, there's an interstellar object hurtling through our solar system. Its name is 3I Atlas, and for months, astronomers have been watching it with a mixture of fascination and unease. They expected it to behave like any other comet passing near the Sun. A little brightening, maybe some outgassing, nothing extraordinary. But in late October, as it reached its closest point to our star, something happened that no one predicted. The surface of this alien visitor began erupting. Not with the gentle release of frozen gases we typically see on comets. This was different. This was violent, organized, powerful. Ice volcanoes, cryovolcanos as scientists call them, began firing jets of material into the darkness of space with such intensity that observatories across Earth captured the spectacle in real time. Let me be clear about what this means. Cryovolcanism is rare, exceptionally rare. In our entire solar system, we've only observed it on a handful of moons, places like Enceladus orbiting Saturn, Europa circling Jupiter, Neptune's bizarre moon Triton. These are worlds where exotic chemistry and extreme gravitational forces create the perfect conditions for ice volcanoes to exist. But those are moons, locked in gravitational dances with massive planets, subjected to tidal heating that keeps their interiors active despite the cold. A comet from another star system? That's not supposed to have the energy, the internal dynamics, or the composition to produce volcanic activity of any kind, let alone ice volcanoes powerful enough to change its brightness significantly. Yet here we are. The observations don't lie. Multiple telescopes recorded the eruptions. The Joan Aurore telescope in Spain caught the initial activity. Follow-up observations confirmed what seemed impossible. 3I Atlas wasn't just passively heating up as it approached the Sun. It was actively erupting from beneath its surface, expelling material with enough force to create visible jets extending thousands of kilometers into space. This wasn't sublimation, the normal process where frozen gases on a comet's surface turn directly from solid to gas as sunlight warms them. This was coming from deep within the object, driven by mechanisms that shouldn't exist on a wandering piece of interstellar debris. Stay with me for the next several minutes, because what I'm about to show you changes everything we thought we understood about interstellar objects, about the building blocks of solar systems, and possibly about the origins of life itself. We're not just talking about unusual comet behavior, we're talking about evidence that challenges fundamental assumptions about how star systems form, what materials they share, and whether the universe operates on more universal principles than we ever imagined. The eruptions on 3I Atlas represent something science has been searching for without quite knowing it. Proof that the chemistry of the cosmos might be far more uniform than our sample size of one solar system suggested. And if that's true, the implications ripple outward in ways that touch everything from planetary formation to the probability of life on distant worlds. But I'm getting ahead of myself. First, you need to understand what happened during those critical days in late October, when 3I Atlas passed through perihelion and began its violent display. Here's what makes this so unsettling. When astronomers first detected the eruptions, their immediate assumption was that they had to be wrong. The data had to be corrupted, equipment malfunction, because the alternative, that an interstellar comet was displaying cryovolcanic activity, violated too many established models. Comets from our own Oort cloud, objects that have orbited the Sun for billions of years, don't typically show this kind of behavior. They outgaze, they shed dust, they develop tails and comas as solar radiation strips material from their surfaces. But volcanic activity, organized eruptions from beneath the surface, that requires energy sources and structural complexity we don't associate with comets. And yet the observations kept coming in, consistent across multiple instruments and observation sites. The spectroscopic data, chemical analysis done by breaking down the light reflected and emitted from 3I Atlas, showed something even more disturbing. The material being ejected from these ice volcanoes wasn't just water ice or simple frozen gases. It contained compounds that told a story about what lies beneath the surface of this visitor from beyond our solar system. Compounds that matched with eerie precision, materials we've only seen in very specific places in our own cosmic neighborhood. Think about what that means for a moment. An object that formed around another star, in a completely different stellar environment, potentially billions of years ago, arrives in our solar system carrying chemistry that mirrors what we see in the most pristine, ancient objects in our own cosmic backyard. It's like finding a stranger on a distant continent who speaks your language fluently, uses your idioms, shares your cultural references, without ever having had contact with your civilization. The probability of that happening by chance, it demands an explanation that reaches deeper than coincidence. The discovery sent shockwaves through the astronomical community, though you wouldn't know it from the muted public response. This wasn't announced with press conferences and dramatic headlines. It emerged gradually through scientific papers and observatory reports published in early December, nearly 6 weeks after the actual perihelion passage. Why the delay? Because scientists were doing what they always do when confronted with data that contradicts established understanding. They were checking, rechecking, and triple-checking their work. They were ruling out instrumental errors, atmospheric interference, contamination from Earth-based sources. They were making absolutely certain that what they were seeing was real before they attached their names to findings that would inevitably invite skepticism. But the data held up. Every test confirmed it. 3I Atlas, this wanderer from another star, was erupting in ice volcanoes, and not just erupting, doing so in ways that revealed a composition and internal structure that challenged everything we thought we knew about the differences between interstellar objects and the materials native to our own solar system. Now, before we go further, I want you to do something for me. Hit that like button if you're as captivated by this mystery as I am, and drop a comment telling me what you think could be powering these eruptions, because the answer, when we get to it, is going to make you question whether the universe is far more interconnected than we ever dared to imagine. And subscribe, because this story is still unfolding in real time, and you're going to want to be here when the next piece of evidence drops. The truth is, we're watching history unfold. We're living in the moment when humanity first encountered direct observable evidence that the building blocks of solar systems might be universal, that the chemistry that created Earth, that created you and me, might not be unique to our corner of the galaxy. 3I Atlas carries secrets from another star system, and those ice volcanoes? They're opening a window into processes and compositions we've never been able to study before. Every eruption is a message, encoded in jets of gas and particles, telling us about conditions around a star we'll never visit, about processes that shaped worlds we'll never see. And here's what keeps scientists up at night. If 3I Atlas matches the chemistry of our own solar system's most ancient objects, what does that say about the formation of every star system in the galaxy? What does it say about the materials available for planet building everywhere? What does it say about the probability that life's raw ingredients, the organic compounds, the water, the complex chemistry necessary for biology, are spread uniformly across the cosmos? These aren't abstract questions anymore. They're questions with observational evidence attached, evidence that's changing answers in real time as we gather more data. And as we approach the critical date, December 19th, when 3I Atlas makes its closest pass to Earth before leaving our solar system forever, the urgency to answer these questions has never been greater. But to understand why these ice volcanoes matter so profoundly, you first need to understand what happened during that pivotal moment in late October, when 3I Atlas reached perihelion and began its spectacular, impossible display. That's where our investigation truly begins, at the point of closest approach to the Sun, where theory collided with reality and lost. Late October marked the moment of truth for 3I Atlas. Perihelion, the point in any object's orbit where it comes closest to the Sun, represents maximum solar heating, maximum stress on the structural integrity of icy bodies, and the time when comets typically become most active. Astronomers had been tracking this interstellar visitor for months, calculating its trajectory, predicting its behavior, preparing observational campaigns to capture every detail of its passage through the inner solar system. They knew perihelion would be important. They had no idea it would be revolutionary. Late October marked the moment. On October 29th, 3I Atlas reached its closest point to the Sun, passing within a region of space where solar radiation becomes intense enough to vaporize even relatively stable frozen materials. For any comet, this is the make-or-break moment. The Sun's heat penetrates the surface, warming layers of ice that have remained frozen for potentially billions of years. Pressure builds as solid ice transitions directly to gas through sublimation. Eventually, that pressure finds release, creating the characteristic fuzzy coma and streaming tails we associate with comets. Scientists expected 3I Atlas to follow this script. Models predicted a gradual increase in brightness as the object approached perihelion, followed by a gradual decline as it moved away from the Sun, and solar heating decreased. There would be outgassing, certainly. The object would develop a coma, the cloud of gas and dust that surrounds an active comet's nucleus. Spectroscopic analysis would reveal the composition of those gases, giving us our first chemical fingerprint of material from another star system. It would be fascinating data, valuable data, but ultimately explainable within the framework of established comet science. That's not what happened. The Jonah telescope, located in Spain and part of the global network of observatories monitoring 3I Atlas, was among the first to detect the anomaly. As perihelion approached, the object did begin to brighten as expected. But the pattern was wrong. Instead of the smooth, gradual increase in luminosity that models predicted, observers saw sudden jumps in brightness, discrete eruption events. The object would maintain a steady state for hours, then abruptly surge in brightness as new material was expelled into space. Then it would stabilize again, only to repeat the pattern. This wasn't passive outgassing. This was active eruption. Episodic, powerful, and completely unexpected for an object of this type. Follow-up observations from other facilities confirmed what the Jonah telescope detected. High-resolution imaging revealed jets of material streaming from specific points on the object's surface. Not a uniform release of gas from all directions, but focused, directional eruptions coming from discrete vents. The telltale signature of volcanic activity, not simple sublimation. Astronomers scrambled to gather as much data as possible during this critical window. Every telescope that could be brought to bear on 3I Atlas was tasked with continuous monitoring. Spectroscopes analysed the light reflected and emitted by the object, breaking it down into component wavelengths to identify the chemical composition of the erupting material. Photometric instruments measured brightness variations with precision, tracking the intensity and duration of each eruption event. Imaging systems captured the geometry of the jets, mapping where on the surface they originated and how they evolved over time. And with each new data set, the picture became more puzzling. The eruptions weren't chaotic or random. They showed structure, repeatability, organization. Specific vents would activate, expel material for a defined period, then go dormant. Other vents would then activate in sequence. It was almost as if the interior of 3I Atlas had chambers of pressurized volatiles that were being released in an organized fashion, as solar heating penetrated deeper into the structure. But that kind of internal organization shouldn't exist in an interstellar comet, an object that presumably formed in the chaotic environment of another star system's planetary disk, and was then ejected into the cold void of interstellar space billions of years ago. The thermal modelling didn't make sense either. For ice volcanoes to operate, you need more than just surface heating. You need internal energy sources or very specific structural configurations that allow pressure to build to eruption levels. In our solar system, the cryovolcanically active moons achieve this through tidal heating. The gravitational pull of their parent planets flexes their interiors, generating friction and heat. 3I Atlas doesn't have a parent planet. It's been travelling through interstellar space, isolated and frozen, for an incomprehensible span of time. Any internal heat it possessed from its formation should have radiated away eons ago. So where was the energy coming from? What mechanism could possibly drive volcanic activity on an object that should be inert, frozen solid throughout its entire volume? The first clues came from chemical analysis of the erupted material. Spectroscopic observations reveal the presence of carbon dioxide ice, which is common in comets and expected. But there was something else. Something that didn't fit the profile of a typical comet nucleus. The spectral signatures showed evidence of carbon monoxide and other highly volatile compounds that require extremely cold temperatures to remain frozen. These supervolatiles, as scientists call them, can exist as ices only in the coldest environments. Their presence suggested that 3I Atlas had remained extraordinarily cold throughout its journey through interstellar space, cold enough to retain materials that would have evaporated from most comets long ago. But here's the paradox. Those supervolatile ices are also extremely reactive to even modest heating. As soon as solar radiation began warming the surface of 3I Atlas at perihelion, those compounds should have sublimated rapidly and uniformly. Instead, they appeared to be erupting from depth, as if the surface layers were protecting internal reservoirs of supervolatiles that remained frozen until eruption events breached the insulating outer shell. This is where the term cryovolcanism became unavoidable. What observers were seeing matched in almost every detail the behaviour of ice volcanoes on moons like Enceladus and Triton. Those moons have subsurface oceans or pockets of pressurised volatile ices beneath protective crusts. When pressure builds sufficiently, either from tidal heating or from the phase change of materials transitioning from liquid to gas, the crust fractures and disruption occurs. The parallels to what was happening on 3I Atlas were unmistakable, except 3. I Atlas isn't a moon. It doesn't have a planet to provide tidal heating. It doesn't have a substantial gravitational field to maintain internal pressure. By all conventional understanding, it shouldn't be capable of sustaining the conditions necessary for cryovolcanism. And yet there it was, erupting before the eyes of astronomers worldwide, defying models and demanding explanation. The scientific community did what it does best in moments like this. It began proposing hypotheses. Maybe 3I Atlas had a highly insulating surface layer that trapped solar heat and created a pressure cooker effect beneath. Maybe the object was larger than initial estimates suggested, with enough mass to retain some internal heat from radioactive decay in its core. Maybe it had a highly porous structure that allowed gases to migrate through channels to eruption vents, concentrating pressure in specific locations. Each hypothesis had problems. Each required assumptions that pushed the boundaries of what we consider plausible for interstellar comets. But the observations were undeniable. The eruptions were real. The cryovolcanism was happening. Which meant that at least one of those seemingly implausible explanations had to be correct, or that something even more exotic was at play. As October turned to November and 3I Atlas began its outbound journey from perihelion, the eruptions didn't immediately stop. The object remained active, continuing to display episodic brightening events consistent with ongoing volcanic activity. This extended activity period gave scientists additional time to gather data, but it also deepened the mystery. Most comets show peak activity right at perihelion and then quickly decline as solar heating diminishes. The fact that 3I Atlas maintained volcanic activity well past its closest approach suggested that whatever mechanism was driving the eruptions didn't depend solely on direct solar heating. Papers began circulating in the astronomical community. Preliminary findings were shared at conferences. The Joan Aurore telescope team published their observations in early December, nearly 6 weeks after the initial detection. The report was cautious, as all good science should be, but the conclusion was inescapable. 3I Atlas had exhibited cryovolcanic activity during its perihelion passage, making it the first interstellar object ever observed to display this phenomenon. But identifying what had happened was only the beginning. The real questions, the ones that would lead to profound implications, were just starting to form. What was the interior composition of 3I Atlas that allowed for this activity? Where did the energy come from? And most critically, what did the specific chemistry of those erupted materials reveal about the object's origin and the environment around the star where it formed? Those answers would require a closer look at what, exactly, was erupting from beneath the surface of this alien visitor. And that's where the story takes its most dramatic turn. Before we can fully grasp why the discovery of ice volcanoes on 3I Atlas is so significant, we need to understand what cryovolcanism actually is, and why it's one of the rarest and most fascinating phenomena in planetary science. Imagine a volcano. Your mind probably conjures images of molten rock, glowing lava flows, explosive eruptions of ash and gas. Earth's volcanoes are powered by internal heat. Radioactive decay in the planet's core and mantle generates temperatures high enough to melt rock, which then rises through the crust as magma and erupts at the surface. This is geology driven by extreme heat, by temperatures that would vaporize any form of water or ice instantly. Now take that concept and invert it. Imagine a world so cold that water doesn't exist as liquid. It's frozen solid, as hard as granite on Earth. Imagine that on this frozen world, the lava isn't molten rock but liquid water, or slush, or highly volatile ices like ammonia or methane. Imagine that the eruptions aren't driven by heat from below but by pressure. Pressure created when subsurface pockets of volatile materials warm just enough to transition from solid to liquid or gas, expanding and seeking release. That's cryovolcanism. volcanoes made of ice, erupting materials that would be frozen solid on most worlds but become fluid or gaseous under the unique conditions of these exotic environments. It's geology at temperatures hundreds of degrees below zero, where ice plays the role of rock, and where the energy sources are subtle enough that they can sustain activity on moons and dwarf planets in the outer reaches of our solar system. We've only seen cryovolcanism in a handful of places. Enceladus, a small moon of Saturn, is perhaps the most famous example. In 2005, NASA's Cassini spacecraft first detected Enceladus's geysers, capturing detailed images during subsequent flybys. These weren't small releases of gas. They were towering plumes of water vapor and ice particles shooting hundreds of kilometers into space. Subsequent observations revealed that Enceladus has a subsurface ocean beneath its icy crust, kept liquid by tidal heating from Saturn's gravity. That ocean occasionally breaches the surface through fissures in the ice, creating the spectacular geysers that have made Enceladus one of the prime candidates in our solar system for harbouring life. Jupiter's moon Europa is another world where cryovolcanism likely occurs, though we haven't observed it as directly as on Enceladus. Europa also has a subsurface ocean, this one potentially containing more water than all of Earth's oceans combined. The icy shell that covers this ocean shows evidence of recent geological activity, ridges, cracks, chaotic terrain that suggests the ice is being fractured and resurfaced by processes below. Some observations have detected plumes of water vapor extending from Europa's surface, suggesting that the subsurface ocean occasionally erupts through the ice in cryovolcanic events. Future missions to Europa will search for active eruptions, and if found, they'll provide a direct window into the ocean below without the need to drill through kilometers of ice. Triton, Neptune's largest moon, presents yet another example, and perhaps the most bizarre. Triton orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. This unusual orbit is almost certainly the result of a gravitational capture event. Triton formed elsewhere in the solar system and was captured by Neptune's gravity. That capture subjected Triton to immense tidal forces that heated its interior, and those forces may continue to provide the energy for cryovolcanic activity observed by Voyager 2 when it flew past in 1989. The spacecraft detected dark plumes erupting from Triton's surface, composed of nitrogen gas and dark organic compounds, rising several kilometers before being swept downwind by the Moon's thin atmosphere. These are the only confirmed examples of cryovolcanism we've observed in our solar system, 3 moons, each orbiting a giant planet, each subject to tidal forces that provide the energy necessary to maintain liquid or semi-liquid interiors beneath frozen crusts. The conditions are extraordinarily specific. You need the right combination of composition, internal heat, and structural configuration to achieve cryovolcanism. It's not something that happens on just any icy body. Which brings us back to 3I Atlas. This isn't a moon. It doesn't orbit a giant planet. It doesn't experience tidal heating. It's been travelling through the frigid emptiness of interstellar space for timescales that boggle the mind. Potentially billions of years isolated from any substantial heat source. Every model we have says it should be frozen solid throughout its entire volume, inert and dead, a chunk of ancient ice and rock that might outgas a bit when warmed by a star but would never, under any circumstances, display the organised, energetic eruptions characteristic of ice volcanoes. And yet here we are, observing precisely that. The eruptions detected during 3I Atlas's perihelion passage match the signatures of cryovolcanism too closely to dismiss. The episodic nature of the activity, the discrete jets emanating from specific surface locations, the spectroscopic evidence of volatiles being released from depth, all of it points to the same conclusion that scientists initially resisted because it seemed impossible. So how does cryovolcanism work mechanically? The process varies depending on the specific environment, but the general principles are consistent. You start with a subsurface reservoir of volatile material, something that can change phase from solid to liquid or gas, with relatively modest changes in temperature or pressure. Water is a common volatile in the outer solar system. So are carbon dioxide, methane, ammonia, nitrogen, and carbon monoxide. These substances freeze at different temperatures, which means they can coexist in layered or mixed configurations within an icy body. When energy is introduced, whether from tidal heating, radioactive decay, or in the case of 3I Atlas, solar radiation, those volatiles begin to warm. As they warm, they undergo phase transitions. Solid ice becomes liquid, liquid becomes gas, and gases, confined beneath an insulating layer of surface ice, build pressure. That pressure seeks the path of least resistance, often finding weaknesses or fissures in the overlying crust. When the pressure exceeds the structural strength of the crust, eruption occurs. The material that erupts depends on the composition of the subsurface reservoir and the temperature and pressure conditions during the eruption. In the case of Enceladus, it's primarily water vapor and ice particles, along with trace organic compounds and salts from the subsurface ocean. For Triton, it's nitrogen gas carrying dark organic material. Each cryovolcano has a chemical signature that reflects the interior composition of its parent body. What makes the 3I Atlas eruptions so scientifically valuable is that they give us a direct sample of the object's interior composition, materials that formed around another star in another stellar environment billions of years ago. Every jet of gas, every particle expelled into space during those eruption events is a messenger carrying information about conditions in a part of the galaxy we can never visit. Spectroscopic analysis of that erupted material is, quite literally, our only way to study the chemistry of another star system's planetary building blocks. And that spectroscopic analysis revealed something that no one expected. Something that changed the entire conversation about what 3I Atlas represents and what its presence in our solar system means for our understanding of cosmic chemistry. But to understand why the chemical composition was so shocking, you need to appreciate what scientists expected to find. Interstellar objects like 3I Atlas should reflect the chemistry of the stellar environment where they formed. Different stars have different metallicities, different abundances of elements heavier than hydrogen and helium. The age of the star, its position in the galaxy, and the chemical composition of the nebula from which it formed all influence what materials are available during planet and comet formation. So scientists expected 3I Atlas to have a unique chemical signature, one that would be noticeably different from objects native to our solar system. What they found instead was a composition that looked eerily familiar, not just similar but in some respects nearly identical to materials found in the most ancient, pristine objects in our own solar system. Materials that represent the original building blocks from which the Sun and planets formed over 4.5 billion years ago. That discovery, the revelation of what exactly was erupting from those ice volcanoes, is where this investigation shifts from fascinating to paradigm challenging, and it's what we need to examine next. The spectroscopic data from 3I Atlas during its active period revealed something that made researchers pause and triple-check their instruments. The erupting material wasn't just composed of simple ices, water, carbon dioxide, methane, the usual suspects we associate with comets. Mixed in with those volatiles were signatures of metals and complex compounds that told a very specific story about what lies beneath the surface of this interstellar visitor: nickel, iron sulfides. These are the chemical fingerprints that appeared in the spectral analysis of material expelled during the cryovolcanic eruptions. Not in trace amounts that could be dismissed as contamination, in concentration significant enough to suggest that 3I Atlas has a core, a central region of the object, composed at least partially of metallic and sulfur-rich compounds, and that core is reacting with the sublimating ices around it in ways that are powering the volcanic activity. Let's unpack why this is so important. Comets in our solar system come in different varieties, but they're generally divided into two broad categories based on their composition and where they formed. You have comets from the Oort cloud, the distant spherical shell of icy bodies surrounding our solar system, and you have comets from the Kuiper belt, the disk of objects beyond Neptune's orbit. Both types contain ices and dust, but their detailed chemistry varies depending on the conditions in the regions where they formed. Most comets are dirty snowballs, a mixture of water ice, frozen gases and silicate dust, with trace amounts of organic compounds and very minor metallic content. They're primitive objects that haven't undergone significant chemical differentiation. They're leftovers from the solar system's formation, chunks of the primordial material that never got incorporated into planets. Their chemistry is relatively simple, because they formed from the nebula of gas and dust that collapsed to create the Sun, and never experienced the temperatures and pressures necessary to create more complex mineral assemblages, but there's a subset of solar system objects that have different chemistry. These are called carbonaceous chondrites when they reach Earth as meteorites, and they represent some of the most primitive, unaltered material in the solar system. Carbonaceous chondrites are rich in carbon compounds, water-bearing minerals, and crucially they contain metal sulfides and sometimes metallic iron-nickel grains. These meteorites are time capsules, preserving the original chemistry of the solar nebula before planets fully formed and altered the chemical landscape through geological processes. The spectroscopic signatures from 3I Atlas match the composition of carbonaceous chondrites with unsettling precision. Specifically, they match a subcategory known as CI chondrites, the Avuna-type carbonaceous chondrites, named after a meteorite that fell in Tanzania. CI chondrites are the most primitive meteorites we've ever found. Their chemical composition matches the Sun's photosphere almost exactly for most elements. They represent the raw materials from which everything in our solar system was built, pristine and unmodified by the high temperatures and pressures that affected most other solar system bodies during formation. Finding this composition in an interstellar object is like discovering that a random stranger's DNA matches your family's genetic markers with extraordinary precision. It's possible theoretically, but it demands an explanation that goes beyond coincidence. The nickel and iron sulfides detected in 3I Atlas's erupted material suggest that the object has a differentiated structure, a core region where heavier metallic compounds have concentrated, surrounded by layers of ices and possibly rocky material. This kind of differentiation requires either formation under specific conditions or enough time and internal heat for gravity to pull dense materials toward the center. The fact that 3I Atlas possesses this structure tells us something important about its formation history. But here's where the chemistry becomes truly fascinating. The iron sulfides in the erupted material appear to be reacting with carbon dioxide ice. This is a well-understood chemical process in laboratory settings. When iron sulfides come into contact with sublimating carbon dioxide ice, oxidation reactions occur. Those reactions release energy, heat, and they can produce gases that contribute to pressure buildup. It's a self-amplifying process. Solar heating causes CO2 ice to sublimate, which brings it into contact with iron sulfides in the core, which produces additional heat and gas, which increases pressure, which leads to more vigorous sublimation and eventual eruption. This mechanism provides a plausible explanation for the energy source driving the cryovolcanism on 3I Atlas. It's not tidal heating, it's not residual formation heat, it's chemical energy, released by reactions between the metallic core and the volatile ices surrounding it. As the object warmed during its approach to perihelion, these reactions initiated and accelerated, creating pockets of pressurized gas beneath the surface that eventually erupted through weak points in the crust. The implications of this mechanism are significant. It means that cryovolcanism doesn't necessarily require the specific conditions we see on tidally heated moons. Any icy body with the right composition, a metallic or sulfide-rich core surrounded by volatile ices, could potentially display volcanic activity when subjected to heating, whether from a star, from radioactive decay, or even from impacts. It expands the environments where we might expect to see active geology on icy worlds throughout the universe. But the real shock wasn't just that 3I Atlas has a carbonaceous chondrite-like composition. It was how closely that composition matches specific objects in our own solar system. Not random Kuiper belt objects, not typical Oort cloud comets. It matches, with disturbing specificity, the chemistry of Trans-Neptunian objects, the population of icy bodies orbiting in the distant reaches beyond Neptune's orbit, remnants from the solar system's formation that never coalesced into planets. When researchers compared the spectroscopic data from 3I Atlas with archival spectra from Trans-Neptunian objects like Pluto, Eris, Makemake, and smaller KBOs, they found matches. Not perfect matches. Every object has some chemical variation based on its specific formation location and history. But the overall pattern of ices, organics, and metallic compounds was strikingly similar. It's as if 3I Atlas could be a sibling to objects in our Kuiper belt, formed from the same cosmic recipe despite originating in an entirely different star system. This is where the discovery transcends astronomy and enters the realm of cosmology and astrobiology. If an object from another star system shares chemistry with our solar system's most primitive objects, what does that tell us about the universality of planetary building blocks? What does it suggest about the conditions in protoplanetary disks around other stars? The conventional understanding has been that every star system is chemically unique to some degree. The metallicity of the parent star, the composition of the molecular cloud from which it formed, the timing of various formation processes, all of these factors should create variation in the chemistry of planets and smaller bodies from one system to another. Yes, the basic building blocks are universal: hydrogen, oxygen, carbon, nitrogen, and so forth. But the relative abundances, the specific compounds that form, the minerals and ices present, those should vary. 3i Atlas challenges that assumption. Its composition suggests that protoplanetary disks, at least those around Sun-like stars, may produce remarkably similar materials regardless of location in the galaxy. The chemistry of planet formation might be more deterministic, more constrained by universal physical and chemical principles than we previously believed. Think about what that means practically. If the building blocks are similar everywhere, then the planets that form from those building blocks will also be similar. Rocky planets in other systems will have similar minerals, similar potential for plate tectonics, similar atmospheric potential. Icy bodies will have similar volatile inventories. And most critically for astrobiology, the organic compounds necessary for life, the amino acids, sugars, lipids, and nucleotides that form the foundation of biochemistry, will be available in similar abundances and configurations throughout the galaxy. The presence of organic compounds in carbonaceous chondrites isn't just trivia. These meteorites contain amino acids, the building blocks of proteins, in significant quantities. They contain nucleobases that form part of DNA and RNA. They contain complex carbon molecules that, on early Earth, likely contributed to the chemical evolution that led to the emergence of life. If 3i Atlas shares this chemistry, it means the raw ingredients for life were present in the star system where it formed, and if those ingredients are present there, they're likely present around countless other stars. This is panspermia territory, not in the sense of living organisms being transferred between star systems, which remains highly speculative, but in the more fundamental sense that the chemical precursors to life are spread uniformly across the galaxy. Life doesn't have to originate through improbable accidents on individual worlds. The chemistry that makes life possible might be built into the fabric of star and planet formation itself, a natural consequence of the physics and chemistry of protoplanetary disks operating under universal laws. The metallic core of 3i Atlas, erupting materials that match our solar system's most pristine meteorites, is telling us that we're not chemically unique. The same processes that built Earth, that delivered water and organics to our world through cometary impacts, that seeded the early planet with the materials necessary for biology, those processes are operating around other stars, and that means the potential for life is not an accident of our specific location in the galaxy. It's a universal possibility enabled by universal chemistry. But there's another layer to this discovery that we need to explore: the specific behavioral and compositional parallels between 3i Atlas and a particular class of objects in our solar system. Objects that occupy the edge of the Sun's influence, preserved in deep freeze for billions of years, representing the most pristine samples of our solar system's birth. Understanding that connection is crucial to grasping the full significance of what these ice volcanoes are revealing. There's a region in our solar system that exists in perpetual twilight, so distant from the Sun that sunlight arrives weakened and faint, taking hours to complete the journey that takes only 8 minutes to reach Earth. This is the realm beyond Neptune, the Trans-Neptunian region, where thousands of icy bodies orbit in a vast belt that extends from roughly Neptune's orbit outward into the beginnings of the Oort cloud. These objects, Trans-Neptunian objects, or TNOs, are time capsules, frozen archives of the solar system's earliest days, preserved in cold storage for over 4 billion years. The Trans-Neptunian region contains several subpopulations. There's the classical Kuiper belt, a disk of objects in relatively circular orbits beyond Neptune. There's the scattered disk, containing objects on more elliptical and inclined orbits, likely scattered outward by gravitational interactions with Neptune during the solar system's youth. And there are the resonant populations, objects locked in orbital relationships with Neptune that protect them from close encounters with the giant planet. Together, these populations number in the hundreds of thousands for objects large enough to detect, and likely in the trillions when you include smaller bodies down to comet-sized chunks. TNOs are fascinating for many reasons, but chief among them is their chemical composition. Because they formed in the coldest regions of the protoplanetary disk and have remained at extreme distances from the Sun ever since, they preserve volatile materials that were lost from the inner solar system. They contain ices that couldn't survive in the warmer environments closer to the Sun, not just water ice, but methane, nitrogen, carbon monoxide, ammonia. They're rich in organic compounds, complex carbon-based molecules created through radiation processing of simpler ices over billions of years, and crucially, they retain the original mineralogy of the solar nebula, unmodified by the heat and pressure that transformed materials closer to the Sun. When scientists obtained the spectroscopic data from 3I Atlas and began comparing it to the spectral libraries of solar system objects, the matches that appeared were striking. The overall spectral profile, the pattern of absorption and emission features across different wavelengths, looked almost identical to spectra obtained from large TNOs. The mix of ices, the presence of organic compounds creating a reddish coloration from long-term radiation exposure, the subtle signatures of complex hydrocarbons, all of it matched the Kuiper belt archetype. More specifically, 3I Atlas's spectrum showed remarkable similarity to objects like Pluto, Eris, and Makemake, the largest known TNOs, dwarf planets in their own right, with complex surfaces and in some cases atmospheres. These bodies represent the largest and most geologically interesting members of the Trans-Neptunian population. Pluto, which NASA's New Horizons mission revealed in stunning detail in 2015, has active geology despite being billions of years old. It has nitrogen ice glaciers, water ice mountains, possible cryovolcanoes, and a hazy atmosphere. Eris, slightly larger than Pluto and more distant, has a bright reflective surface suggesting recent resurfacing by volatile ices. Makemake is covered in methane and nitrogen ices that somehow avoid sublimating away despite surface temperatures that should allow gradual loss. The fact that 3I Atlas shares compositional characteristics with these objects is profound. TNOs formed from the raw materials of our solar system's protoplanetary disk. They represent the original mix of materials present in the outer regions, where giant planet formation occurred. Their chemistry tells us what ingredients were available when the solar system was young, what compounds survived from the molecular cloud that collapsed to form the Sun. And now we have an object from another star system with matching chemistry. Not vaguely similar, not in the same ballpark. Matching with enough precision that if you didn't know 3I Atlas was interstellar, you could reasonably mistake its spectrum for that of a Trans-Neptunian object. What does that match tell us? It tells us that the outer regions of protoplanetary disks, the cold zones beyond where ice giants form, produce remarkably consistent chemistry across different star systems. The temperature and pressure conditions in those regions are constrained by physics. At certain distances from a Sun-like star, water ice condenses from the nebular gas. Further out, carbon monoxide and nitrogen ice become stable. Further still, even hydrogen and helium ices can form under the right conditions. These boundaries are determined by fundamental thermodynamics and the radiative properties of young stars. If those boundaries are similar for all Sun-like stars, then the chemistry that develops in different annular zones of protoplanetary disks will be similar. The same minerals will condense at the same temperatures. The same ices will accumulate in the same regions. The same organic compounds will form through the same radiation-driven chemistry. And the bodies that eventually accumulate from these materials, planets, dwarf planets, comets, asteroids, will have similar compositions regardless of which star system they formed in. This is what 3I Atlas is confirming. It's not just that building blocks are universal in a vague sense. It's that the specific assemblages of materials, the particular combinations of ices, organics, and minerals that make up icy bodies in the outer solar system, are replicated in other stellar systems. The recipe for Trans-Neptunian objects isn't unique to our solar system. It's a universal recipe followed by any protoplanetary disk around a Sun-like star. The implications ripple outward in multiple directions. For planetary science, it means we can study TNOs in our own solar system and learn not just about our history, but about the composition and evolution of icy bodies throughout the galaxy. Every mission to Kuiper belt objects, every spectroscopic observation of distant TNOs, contributes to a database of information applicable to planetary systems we'll never visit. The New Horizons mission to Pluto wasn't just exploring one world, it was, in a sense, exploring a universal class of objects that exists around countless stars. For cosmochemistry, it means the chemical evolution pathways we see in our solar system, the formation of complex organics through radiation processing, the alteration of minerals through ice-rock interactions, the delivery of volatiles to inner planets through cometary impacts, are happening elsewhere. The same processes that enriched Earth with water and organic compounds in its early history are enriching rocky planets around other stars. The same chemical evolution that set the stage for life's emergence here is setting the stage for potential biogenesis throughout the galaxy. For astrobiology, the implications are perhaps most exciting. If TNO-like objects are common around other stars, then the delivery of life's building blocks to planets in habitable zones is also common. The organic compounds found in carbonaceous chondrites and observed on TNOs, amino acids, sugars, complex hydrocarbons, don't have to be synthesized from scratch on every planet where life might emerge. They can be delivered pre-formed, accumulated over millions of years through impacts of comets and asteroids that formed in the outer reaches of those systems. This doesn't guarantee life elsewhere. The gap between having the right chemical ingredients and achieving actual living systems is vast and not fully understood, even for Earth's history. But it removes one major uncertainty. We now have evidence that the chemical prerequisites for life aren't rare or special. They're a natural consequence of star and planet formation. Every system with a sun-like star likely has an outer region full of icy bodies with chemistry similar to our Kuiper belt, and those bodies can deliver that chemistry to inner planets. The behavioral similarities between 3I Atlas and TNOs extend beyond just composition. Large TNOs show geological activity despite their small size and immense distance from the Sun. Pluto has active nitrogen ice convection, meaning its surface is being continuously recycled by slow-motion glaciers of nitrogen ice flowing over the landscape. Triton, which is almost certainly a captured TNO, has active geysers as we discussed earlier. These activities are driven by exotic heat sources, radioactive decay, tidal heating in Triton's case, and possibly chemical reactions between ices and rocky materials in the interior. The cryovolcanism on 3I Atlas fits this pattern. It's showing us that TNO-class objects, whether they orbit our Sun or formed around another star, have internal dynamics and chemistry that can sustain geological activity under the right conditions. They're not dead, inert ice balls. They're complex bodies with layered interiors, chemical reactivity, and the potential for sustained activity over geological timescales. This reframes how we think about habitability in the outer reaches of planetary systems. For decades, the discussion of habitable zones, the regions around stars where liquid water can exist on a planet's surface, has focused on rocky planets at specific distances from their stars. But subsurface habitability is a different paradigm. Moons like Enceladus and Europa, despite being far outside the traditional habitable zone, have liquid water oceans beneath their icy shells. The energy to maintain those oceans comes from tidal heating, but other energy sources are possible: radioactive decay, chemical reactions, residual heat from formation. If TNO analogues around other stars have similar internal compositions to our Kuiper belt objects, and if some of them have metallic or sulfideric cores like 3I Atlas appears to have, then those bodies could maintain subsurface liquid water through chemical heating. They could potentially remain habitable for billions of years, long after their parent stars have died, simply by sustaining chemical reactions between their cores and surrounding ices. This is speculative but not unreasonable. The point is that 3I Atlas is opening conceptual doors. It's showing us that icy bodies across the galaxy might be far more geologically and chemically active than we assumed. It's suggesting that the outer reaches of planetary systems aren't frozen, dead zones, but dynamic environments where complex chemistry and possibly even biology could persist in subsurface environments we're only beginning to consider. The match between 3I Atlas and our Trans-Neptunian objects also raises an interesting historical question. Our solar system has captured objects before. Neptune's moon Triton, as mentioned, is almost certainly a captured TNO, seized from independent orbit around the Sun by Neptune's gravity sometime in the solar system's past. Could our solar system capture an interstellar object? Could 3I Atlas, or something like it, end up in a permanent orbit around the Sun? The dynamics are challenging. Interstellar objects enter the solar system with hyperbolic trajectories. They're moving too fast to be captured by the Sun's gravity alone. For capture to occur, they'd need to lose energy somehow, typically through a gravitational interaction with a planet that slows them down enough to become gravitationally bound. It's rare but not impossible. Some dynamical studies suggest that over the age of the solar system, our Sun might have captured a small number of interstellar objects that now orbit in the Oort cloud or Kuiper belt, indistinguishable from native objects except through detailed chemical analysis that we can't yet perform. If that's true, then some of the TNOs we study might actually be immigrants from other star systems, bearing chemistry from their birth systems that happens to match ours closely enough that we can't tell the difference. The universe might be more interconnected than we realize, with material exchange between star systems occurring over billions of years through the slow migration of interstellar objects. 3. I-Atlas won't be captured. Its trajectory and velocity make that impossible. It will pass through our solar system and return to interstellar space, continuing a journey that has no destination, wandering the galaxy for potentially billions more years until it encounters another star system or is disrupted by some gravitational interaction we can't predict. But it has given us something invaluable, proof that our solar system's chemistry isn't unique, that the building blocks we're made of exist in similar configurations throughout the galaxy, and that the processes we see in our cosmic neighborhood are reflections of universal patterns operating on galactic scales. Yet even with this understanding, there are pieces of the puzzle that don't fit, observations that remain unexplained, and questions that the straightforward compositional analysis doesn't fully answer. And that's where we need to go next, into the realm of the unknown, the unexplained. The genuinely mysterious aspects of 3I Atlas that even the remarkable TNO similarity doesn't completely resolve. Science is at its most honest when it acknowledges what it doesn't know. And despite the remarkable insights we've gained from studying 3I Atlas and its cryovolcanic eruptions, there remain observations that puzzle researchers, behaviours that don't quite fit the models, and mysteries that even the TNO composition analogy doesn't fully explain. These unresolved questions are where the story gets truly fascinating, and where speculation, both conservative and controversial, enters the picture. Let's start with what remains genuinely unexplained. The first puzzle is the timing and intensity of the eruptions. Yes, we have a plausible mechanism, chemical reactions between iron sulfides and sublimating carbon dioxide ice-creating pressure and heat. But the episodic nature of the eruptions, the specific timing of peak activity, and the sustained activity well past perihelion don't perfectly match what models predict for this mechanism. There seems to be an organizational principle to the eruptions that we're missing, some structural aspect of 3I Atlas's interior that controls where and when pressure is released. Some researchers have suggested a porous, sponge-like interior structure that would allow gases to migrate through channels before erupting from specific vents. Others propose a layered internal structure with different volatile reservoirs at different depths, each becoming active as solar heat penetrates deeper into the object. These are reasonable hypotheses, but we don't have direct evidence for any particular internal structure. We're inferring based on surface observations, which always involves uncertainty. Then there's the brightness variation. Beyond the eruption-related brightening, 3I Atlas has shown subtle fluctuations in reflected light that suggest either surface albedo variations as different faces rotate into view, or potentially even more exotic phenomena. Some researchers noticed what they described as a pulse in the light curve, a regular rhythmic variation that occurred on a specific timescale. This could be simple rotation, with bright and dark patches on the surface creating a predictable pattern as the object spins. But the specific characteristics of the variation made some observers wonder if something more complex was happening. This is where we enter the territory of Avi Loeb, the Harvard astrophysicist who has become both celebrated and controversial for his willingness to propose exotic explanations for astronomical observations. Loeb has been tracking interstellar objects with intense interest since Oumuamua, the first detected interstellar visitor, exhibited unusual acceleration that some interpreted as outgassing, but that didn't produce the expected visible coma. Loeb controversially suggested that Oumuamua might be an artificial object, a light sail from another civilization, based on its shape and motion. With 3I Atlas, Loeb has been more measured, but no less intrigued. He's noted the cryovolcanic activity with interest, but he's also pointed out aspects of 3I Atlas's behaviour that don't have definitive natural explanations. the specific pattern of brightness variations, the intensity of eruptions relative to the object's size, the apparent sustainability of activity over a time frame longer than models easily explain. To be clear, Loeb isn't claiming 3. IATLAS is artificial or that aliens are involved. He's simply noting that our models for interstellar cometary behaviour might be incomplete, and that we should remain open to unexpected physical processes we haven't yet characterised. The scientific community's response to Loeb's approach is mixed. Some appreciate his willingness to question assumptions and to propose that we take seriously the possibility of technological artefacts in space. Others feel his public statements venture too far into speculation without sufficient evidential foundation, risking public misunderstanding of how science actually operates. The debate is healthy, though, because it forces the community to articulate exactly what evidence would be required to support different hypotheses and to be explicit about the difference between unexplained and impossible to explain naturally. For 3I Atlas, the current consensus is that while there are unexplained details, nothing about its behaviour requires exotic explanations. Cryovolcanism driven by chemical reactions is unusual, but not unprecedented in principle. The compositional match with TNOs suggests a natural origin and evolution within a protoplanetary disk around another star. The eruptions, while dramatic, are explainable with physics and chemistry we understand. The mysteries that remain are more likely due to gaps in our knowledge about cometary interiors and the detailed physics of cryovolcanism than to anything truly anomalous. But let's acknowledge what we genuinely don't understand. We don't know exactly how large 3I Atlas is. Estimates vary depending on assumptions about albedo, how reflective its surface is, and we can't measure its size directly without resolved imaging, which requires it to be much closer than it ever got to Earth. Different size estimates lead to different models of its internal structure and energy budget. A larger object could retain more internal heat from formation, or have more radioactive elements contributing to heat production. A smaller object would need more efficient mechanisms to sustain the observed activity. We don't know its precise rotation state. We have estimates based on light curve analysis, but without detailed resolved imaging, we can't be certain about its spin axis, rotation period, or whether it's tumbling chaotically or rotating stably. Rotation matters because it affects how solar heating is distributed across the surface, and how internal stresses from that heating might organise within the structure. We don't fully understand its trajectory history. We can calculate where it is and where it's going with high precision, but we can only estimate where it came from. Backtracking its motion through the galaxy involves uncertainties, because we don't know what gravitational perturbations it might have experienced during its interstellar journey. Different possible origin points would mean different ages, different radiation exposure histories, different probabilities of having encountered other stars during its wandering. All of that context would help us interpret what we're seeing now. And then there's the question of how common objects like 3I Atlas actually are. We've now detected a handful of interstellar objects passing through our solar system. The detection rate suggests there could be trillions of such objects in the galaxy, far outnumbering the stars themselves. If true, that has profound implications for galactic ecology. It means star systems aren't isolated, they're continuously exchanging material. Comets ejected from one system eventually encounter others. Over billions of years, the cumulative effect of this exchange could be significant. Some scientists have proposed that this material exchange could facilitate panspermia, the transfer of life or its precursors between star systems. If comets like 3I Atlas are common, and if they carry complex organic chemistry as we've discussed, then impacts of such objects on planets in habitable zones would deliver that chemistry. If any of those objects carried actual microbial life preserved in ice, protected from radiation by meters or kilometers of shielding, then life itself could potentially spread between systems over cosmic timescales. This is highly speculative, and there are substantial obstacles to interstellar panspermia, exposure to cosmic radiation and high-energy particles being chief among them. But the discovery that interstellar objects share chemistry with local populations makes the hypothesis at least worth considering. It's no longer purely in the realm of science fiction. There's also the unsettling question of what we're missing. 3I Atlas was bright enough and large enough to detect, and it passed reasonably close to the Sun, making it active and observable. But how many interstellar objects pass through the solar system undetected because they're smaller, darker, or on trajectories that don't bring them close enough to the Sun to activate. The detection bias is severe. We only see the brightest, most active visitors. The true population could be vastly larger, with 3i Atlas representing just the tip of an enormous iceberg. If that's the case, then our solar system is essentially swimming in interstellar debris, constantly being traversed by objects from other stars. Most would be small, boulder-sized to building-sized, and totally invisible to our current detection systems. But they'd be there, silently passing through, occasionally captured by planetary gravity, sometimes impacting moons or planets without us ever knowing their interstellar origin. This connects to another open question. Has Earth been hit by interstellar objects? In principle, yes, almost certainly. Over the age of the solar system, the statistical probability of interstellar impacts on Earth is high. But identifying a specific meteorite or impact crater as being of interstellar origin is nearly impossible. By the time an interstellar object impacts Earth, it's been heated during atmospheric entry, and any trajectory information that could identify its origin is lost in the violence of impact. The chemistry might be unusual, but unusual chemistry alone isn't proof of interstellar origin. It could just indicate formation in an unusual part of our own solar system. What we need to resolve these mysteries is more data, and that means more observations, which brings us to the critical upcoming event that might answer some of these questions, or raise even more compelling new ones. Mark your calendar. December 19th. That's the date when 3i Atlas makes its closest approach to Earth, before leaving our solar system forever. This isn't just another point on the object's trajectory. It's our final opportunity to gather detailed observations, to answer lingering questions, and to extract every possible bit of information from this visitor before it vanishes back into interstellar space. The geometry is important. On December 19th, 3i Atlas will pass within a certain distance of Earth, close enough that ground-based telescopes will have their best viewing conditions, but not so close as to be dangerous in any way. The object will be well positioned for observation from multiple locations around the globe, allowing continuous monitoring as Earth rotates. Weather permitting at key observatory sites, we'll have an unprecedented window to study an interstellar object under optimal conditions. What makes this moment critical is that after December 19th, 3i Atlas begins its journey back out of the solar system in earnest. It will fade rapidly as distance increases and solar illumination decreases. Within weeks, it will become too faint for all but the largest telescopes to detect. Within months, it will be lost to observation entirely, swallowed by the darkness of space from which it emerged. This is our last chance. Observatories around the world have planned coordinated campaigns to maximize the scientific return from this closest approach. Telescopes across multiple wavelengths, optical, infrared, radio, will be pointed at 3i Atlas simultaneously, gathering complementary datasets that can be combined for a comprehensive picture. Spectroscopes will capture high-resolution spectra to refine our understanding of its composition. Imaging systems will attempt to resolve surface features if the object is large enough and close enough for any detail to be visible. Photometric monitoring will track brightness variations with precision to constrain rotation and search for any additional eruption events. Ground-based telescopes and space observatories worldwide are preparing intensive observation campaigns. From above Earth's atmosphere, Hubble can achieve angular resolution and sensitivity impossible for ground-based instruments. If 3i Atlas is large enough, and if conditions are favourable, Hubble might resolve it as more than just a point of light, perhaps a few pixels showing shape or at least orientation. Even crude resolved imaging would dramatically improve our understanding of its structure. Ground-based instruments have their advantages too. Large telescopes like those at Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Gran Telescopio Canarias in Spain can gather enormous amounts of light, crucial for spectroscopy of a relatively faint object. These facilities can also respond quickly to transient events. If 3i Atlas undergoes another major eruption episode during the December 19th approach, observers can rapidly reconfigure instruments to capture the event in detail. What do scientists hope to learn during this critical window? Several key questions remain open. First, confirmation of the object's size and albedo. With better angular resolution at closest approach, it may be possible to directly measure how much area 3i Atlas presents to us, which combined with brightness measurements gives us its reflectivity. That resolves the uncertainty about whether it's a relatively large, dark object or a smaller, brighter one, a crucial parameter for understanding its composition and structure. Second, definitive characterization of its rotation state. Continuous monitoring during closest approach will provide the best light curve data yet, potentially revealing rotation period, axis orientation, and whether the rotation is simple or complex. This matters for modelling how solar heating distributes across its surface and how internal stresses develop. Third, detection of any ongoing activity. Is 3I Atlas still erupting? The last detailed observations were from early December, weeks after perihelion. If the object remains cryovolcanically active at the December 19th approach, it would indicate that the driving mechanism doesn't depend solely on maximum solar heating, but has sustained internal processes. Conversely, if activity has ceased, that constrains how quickly the chemical reactions powering the eruptions exhaust their available materials. Fourth, more precise trajectory refinement. As 3I Atlas passes close to Earth, our gravitational influence, tiny though it is, will slightly perturb its path. Measuring that perturbation with precision allows us to calculate its mass, which combined with size estimates gives us density, a critical parameter for understanding composition. Is it a dense, rocky metallic object with an icy coating? Or is it a low-density, porous structure like many comets in our solar system? The excitement in the astronomical community is palpable. Researchers who've dedicated months to studying 3I Atlas are preparing for this culminating observational campaign. Students are being trained to operate instruments and process data rapidly as it comes in. Computational models are being readied to compare predictions with observations in real time. There's a genuine sense that December 19th could yield discoveries that reshape our understanding of this object. But there's also an undercurrent of melancholy. After this date, 3I Atlas is gone. Unlike objects in our solar system that we can observe repeatedly over years or decades, refining our knowledge with each observing season, interstellar visitors offer only one chance. What we learn by December 20th is all we'll ever learn from direct observation. Future insights will come only from analysing the accumulated data, looking for patterns or details that weren't apparent in an initial analysis. This finite opportunity is driving some observers to propose ambitious, even risky, observing strategies. Should we use every available minute of telescope time on 3I Atlas, potentially at the expense of other scientific programs? Should observatories coordinate to provide continuous coverage, accepting that this means some facilities will be observing during less than ideal conditions? How much redundancy is appropriate? How many different instruments should be capturing essentially the same data to ensure nothing is lost to equipment failure or bad luck? These are the practical questions being debated in the weeks leading up to closest approach, but for those of us watching from outside the professional community, the moment represents something more. It's a reminder of the transient nature of these cosmic encounters, the preciousness of opportunities to study the universe's mysteries when they present themselves. 3. I Atlas travelled light years to reach us, spent a few months in our observational range and will vanish again into the void. It's here, briefly, like a traveller passing through a small town, and then it's gone. There's poetry in that. For billions of years, 3I Atlas wandered through darkness, perhaps never approaching a star closely enough to warm its surface or trigger eruptions. Then it entered our solar system, felt the sun's heat for the first time in eons, and responded with violent eruptions that revealed its secrets to curious observers on a small planet it would never visit. And now it leaves, returning to the cold and dark, those eruptions fading to nothing, the object once again becoming a frozen inert relic drifting between the stars, unless, of course, it eventually encounters another stellar system. Perhaps in 100 million years, 3I Atlas will approach another sun-like star, warming once again, erupting once again, potentially being observed by astronomers from another world who wonder about its composition and origins just as we do now. The universe works on timescales that dwarf human comprehension, and this single object may have a history and future that spans billions of years and countless stellar encounters. But for us, this is it. December 19th, our moment with 3I Atlas, and whatever we discover during that closest approach will have to sustain our curiosity and answer our questions, because there are no second chances with interstellar visitors. As the date approaches, the data will flow in, and we'll learn whether our theories about its composition, structure, and activity are correct. We'll see if there are surprises waiting, observations that don't fit expectations, mysteries that deepen rather than resolve. And then, shortly after, 3i Atlas will fade from view, leaving us to contemplate what its brief visit has taught us about the universe we inhabit, which brings us to perhaps the most important question of all. What does all of this mean for us? Step back from the technical details for a moment. Step back from the spectroscopy and the orbital mechanics and the cryovolcanic mechanisms. Look at the larger picture that 3i Atlas is painting for us. What does it mean, truly mean, that an object from another star system shares chemistry with our own solar system's most ancient bodies? What does it tell us about our place in the universe, about the origins of the materials that make up our world, and about the potential for life beyond Earth? The philosophical implications are profound. For most of human history, Earth was understood to be unique, special, the centre of creation. That geocentric worldview collapsed when Copernicus demonstrated that Earth orbits the Sun, not the reverse. But even then, our solar system was considered unique, or at least special. We were the planetary system, the only one we knew about. That assumption eroded further with the discovery of exoplanets beginning in the 1990s. We now know that planets are common, that most stars have planetary systems, that the galaxy contains hundreds of billions of worlds. Earth is not unique in being a planet, but perhaps, we thought, Earth's chemistry is special. Perhaps the specific combination of elements and compounds that allowed life to emerge here is rare, requiring unusual circumstances. 3. Atlas tells us that even that assumption is probably wrong. The chemistry that built Earth, the water, the organic compounds, the minerals, the metallic core, is not unique to our solar system. It's replicated in at least one other system, likely in many systems, perhaps in most systems around Sun-like stars. The recipe for Earth-like worlds, at least in terms of raw materials, is universal. Think about what that means for the origin of life. One of the great uncertainties in astrobiology has been whether life's chemical precursors are common. We know life arose on Earth, but we haven't known whether that required a lucky accumulation of rare molecules, or whether the building blocks of life are present on every rocky planet as a matter of course. The discovery of complex organic compounds in meteorites suggested the latter, but meteorites are from our own solar system. Maybe our system was chemically unusual in producing those organics. 3i Atlas suggests otherwise. If an interstellar object has similar organics, then the processes that create those compounds, radiation, processing of simple ices, chemical reactions in liquid water environments within icy bodies, accumulation of carbon compounds in protoplanetary disks, are operating universally. Life's ingredients are everywhere. That doesn't guarantee life is common, because we still don't fully understand the steps from complex chemistry to actual living systems. But it removes one major potential barrier. The chemical prerequisites for life are not a bottleneck. They're provided by the universe as standard equipment on ice worlds. This has practical implications for how we search for life. If icy bodies throughout the galaxy have similar chemistry to our Kuiper Belt objects, then planets in habitable zones around other stars are being seeded with water and organics through cometary impacts just as Earth was. Those impacts are delivering not just raw elements, but preformed complex molecules that can jumpstart chemical evolution toward biology. Every star system has its own version of the late heavy bombardment that pummeled Earth in its youth, and every bombardment delivers the same basic toolkit of life's ingredients. The search for life beyond Earth has focused heavily on finding planets in the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface. That focus is justified because liquid water is essential for life as we know it. But 3i Atlas reminds us that habitability might extend far beyond those zones. If icy bodies in the outer reaches of other systems have internal chemistry capable of driving cryovolcanism, then they might also have subsurface liquid water maintained by chemical or radioactive heat. Life could potentially exist in those subsurface oceans, completely independent of surface conditions or proximity to the star. This is the paradigm exemplified by moons like Enceladus and Europa in our own system. Enceladus has a global subsurface ocean. liquid water in contact with a rocky core where chemical reactions can produce energy, and active geysers that spew ocean water into space where we can sample it. If Enceladus harbours life in that ocean, it would demonstrate that life doesn't need a planet's surface or sunlight. It just needs liquid water, energy sources, and the right chemistry, all of which can exist deep beneath ice shells on moons or dwarf planets far from stars. If Enceladus analogues exist around other stars, and if they have TNO-like chemistry as 3I Atlas suggests is possible, then the number of potentially habitable environments in the galaxy skyrockets. Every star system might have dozens or hundreds of icy moons or dwarf planets with subsurface oceans. The total volume of liquid water in the galaxy, the total available habitat for life, could be vastly larger than we've been assuming when we focus only on surface habitats on rocky planets. 3I Atlas is also teaching us about cosmic connectivity. For most of history, star systems have been thought of as isolated islands in space. Material stays within its birth system, orbiting its star for billions of years until the star's evolution destroys or ejects it. But the existence of interstellar objects in significant numbers and the growing realization that they might be extremely common suggests that star systems are more like interconnected nodes in a network. Material is constantly being exchanged, albeit slowly, through the ejection and capture of comets and other debris. Over the age of the galaxy, this exchange could have profound effects. Stars move through the galaxy, occasionally passing close enough to other stars that their Oort clouds intermingle, swapping comets. Interstellar objects like 3I Atlas wander until they encounter a new system, sometimes being captured into orbit. Slowly, over billions of years, the galaxy mixes its materials. Chemistry that originated in one star system spreads to others, isotopic signatures, trace elements, even potentially biological molecules get distributed. This galactic ecology means that in a sense, we're all made of recycled star stuff not just from our own sun, but from previous generations of stars whose ejected materials were incorporated into the nebula that formed our solar system. And now we're learning that we might also contain materials from other contemporary star systems, delivered by interstellar objects that collided with Earth early in its history. We're not isolated. We're part of a galactic community of matter and chemistry that transcends individual stellar systems. There's something humbling and beautiful about that realization. The atoms in your body were forged in ancient stars, sure, that's been known for decades. But some of those atoms might have been part of planets or comets around other stars before they ended up here. The oxygen you're breathing, the carbon in your bones, the iron in your blood, these atoms have histories that might include time in other solar systems. You're made of the galaxy, not just of the sun's local materials. 3I Atlas is a messenger bringing this reality into focus. Its chemistry, so similar to our own solar systems, is evidence of the underlying unity of cosmic processes. The universe isn't a collection of unique, isolated systems. It's an interconnected whole, where the same physical laws, the same chemical reactions, the same evolutionary pathways operate everywhere. We're learning that the story of any one planet, including Earth, is inseparable from the larger story of galactic chemical evolution. This should change how we think about exploring space. When we send missions to Kuiper Belt objects, we're not just studying our own system's history, we're studying universal processes that apply to icy bodies around every star. When we analyze meteorites in the lab, we're not just learning about our solar system's formation, we're learning about planet formation as a universal phenomenon. Every piece of data we gather has implications that extend beyond our local environment, and when we eventually develop the capability to study exoplanets in detail, to analyze their atmospheres, to detect biosignatures, perhaps even to directly image their surfaces, we'll be interpreting those observations through the lens of knowledge built right here. The lessons from 3I Atlas and other interstellar visitors will inform our understanding of what we're seeing around other stars. We'll know that icy bodies there likely have similar chemistry to ours, that delivery of water and organics to inner planets probably follows similar patterns, that the potential for life exists not just on planets, but throughout entire systems wherever liquid water and chemistry intersect. The story of 3I Atlas is ultimately a story about unity and diversity. The universe is vast beyond comprehension, filled with countless star systems, each forming and evolving in its own way. But underlying that diversity is a unity of process and outcome. The same building blocks appear everywhere, the same chemistry unfolds, The same potential for complexity, organization, and perhaps life exists throughout. We're not alone in the universe, even if we haven't found other civilizations yet. We're surrounded by kinship at the molecular level, by materials and chemistry that mirror our own everywhere we look. 3i Atlas is family in a sense. Distant family from a system we'll never visit, but family nonetheless, built from the same cosmic ingredients through the same universal processes. And that brings us to the end of our journey, though not to the end of the story, because the story of 3i Atlas is still being written, and you're part of it. We started this journey with an impossibility: ice volcanoes erupting on an object from another star, something that shouldn't exist but undeniably does. We've followed the evidence through layers of discovery. The perihelion eruptions that revealed cryovolcanism, the metallic core chemistry that explained the energy source, the stunning similarity to Trans-Neptunian objects that rewrote our assumptions about cosmic chemistry. And we've explored the implications, reaching toward understanding what it all means for our place in the universe and the prevalence of life beyond Earth. But here's the truth that science always demands we acknowledge. We don't have all the answers. Not yet. December 19th will provide more data, and that data will answer some questions while undoubtedly raising others. The analysis of 3i Atlas will continue for years as researchers mine the observations for details that weren't apparent in initial reviews. New theories will emerge, some current interpretations will be refined or overturned. That's how science works, not through sudden revelations of complete truth, but through incremental progress toward deeper understanding, each observation adding another piece to an ever-expanding puzzle. What we do know is that 3i Atlas has already changed how we think about interstellar objects. It's demonstrated that these visitors aren't just curiosities to be catalogued and dismissed. They're data streams carrying information about parts of the galaxy we can never reach, about chemistry and processes that operate beyond our direct observation. Every interstellar object detected is an opportunity, a free sample of another star system delivered to us for study. We need to seize these opportunities because they're fleeting and precious. The coming years will likely bring more detections. Survey telescopes designed to scan the sky for transient events, objects that appear, change, or move, are coming online or improving their capabilities. Projects like the Vera Rubin Observatory, with its massive field of view and sensitive detectors, will discover far more interstellar objects than we've found to date. Each one will contribute to our understanding of what's out there, what chemistry exists across the galaxy, how common different types of objects are, and perhaps, eventually, we'll detect an interstellar visitor that's truly anomalous, something that can't be explained by natural processes, that demands consideration of more exotic possibilities. If that day comes, the careful scientific work done on objects like 3i Atlas will provide the baseline for recognizing genuine anomalies. We'll know what normal interstellar comets look like, how they behave, what chemistry they should have. Deviations from that baseline will stand out clearly, demanding explanation. But even if every future interstellar object turns out to be natural, as is overwhelmingly likely, each one enriches our understanding. Each one is a gift from the cosmos, offering insights we couldn't gain any other way. The universe is revealing its secrets to us one wandering comet at a time, and we're learning that those secrets point toward an underlying unity we're only beginning to appreciate. For you, the person who's stayed with me through this entire exploration, I hope this story has sparked something. Maybe it's curiosity about astronomy, a desire to learn more about how we study objects in space. Maybe it's wonder at the scales involved, the billions of years, the light years of distance, the incomprehensible number of stars and planets in the galaxy. Maybe it's a philosophical reflection on what it means that we're made of stardust not just metaphorically, but literally, that the materials of our world are shared across the galaxy. Whatever you take from this, hold on to it. We live in an extraordinary era. For the first time in human history, we have the capability to detect objects from other star systems and analyze them in detail. We can peer into the atmospheres of planets around distant stars. We're planning missions to potentially habitable moons in our own solar system. We're on the cusp of answering questions that philosophers and scientists have debated for millennia. Are we alone? Is life common? What is our place in the cosmic story? 3. 3i Atlas is a small piece of that larger endeavour, but it's an important piece. It's teaching us that the universe is more coherent, more uniform, more connected than we realized. It's showing us that the chemistry of life's origins isn't rare or special, but potentially universal. And it's reminding us that we're participants in a cosmic drama that extends far beyond our small planet, far beyond our brief moment in time. As December 19th approaches and then passes, as 3i Atlas fades from our telescopes and returns to the darkness between stars, take a moment to appreciate what we've witnessed. An ancient wanderer from unknown origins, travelling for untold eons through the void, passed through our neighbourhood, and in doing so revealed secrets about the universe's fundamental nature. We were here to see it. We had the technology to study it. We asked the right questions and gathered the data to answer some of them. That's a privilege, a cosmic coincidence of timing that allowed us to be part of this story. The universe will send other messengers. There will be more interstellar visitors, more discoveries, more moments when our understanding shifts and expands. If you want to be part of that ongoing story, if you want to witness the next revelation when it comes, then stay engaged. Follow the science, support the missions and telescopes that make these discoveries possible, ask questions, maintain your sense of wonder, and right now help this particular story reach others. Hit that like button if this exploration resonated with you. It tells me that deep dives into cosmic mysteries are valuable to you, and it helps others find this content. Drop a comment sharing what aspect of 3i Atlas fascinates you most. Is it the ice volcanoes themselves, the chemical similarity to our solar system, the implications for life elsewhere, or something else entirely? I read every comment, and your perspectives often spark ideas for future videos. Subscribe to this channel if you haven't already, because I'll be following up on 3i Atlas as new data emerges. When the December 19th observations are processed and published, I'll break down what we learned and what new questions arose. When the next interstellar object is detected, and there will be a next one, I'll be here to explore its story with you. This is an ongoing conversation about our place in the universe, and I want you to be part of it. Share this video with someone who would appreciate it. Send it to that friend who loves space, to the family member who asks deep questions about existence, to the colleague who's curious about science but doesn't know where to start. These stories are for everyone, not just specialists. The discoveries happening in astronomy right now are humanity's discoveries, and everyone deserves access to them in a form that's engaging and comprehensible. The story of 3i Atlas is our story. The story of a species that has learned to read the messages written in starlight and cosmic visitors, that can interpret chemistry and motion to reconstruct events from billions of years ago and billions of miles away. We're the universe's way of understanding itself, as Carl Sagan reminded us, and right now, we're understanding that we're made of materials that are spread throughout the galaxy, that our existence is not an accident of unique chemistry, but a probable outcome of universal processes. That's a profound realization, and it comes to us courtesy of a wandering chunk of ice and rock that happened to pass through our solar system at a moment when we had the capability to study it. Thank you for taking this journey with me. Thank you for caring about ice volcanoes on distant comets and what they reveal about the cosmos. Your curiosity, your willingness to engage with these ideas, is what makes this work meaningful. Keep looking up, keep asking questions, and I'll see you in the next video when we explore whatever mystery the universe reveals next. Until then, remember that you're made of star stuff, connected to the cosmos in ways both literal and profound, and that every discovery in astronomy is a discovery about you and where you came from. The universe is vast and ancient, but it's also intimate and personal, because you're part of it. Never forget that.